So here we're going to continue our discussion of Koopman operator for linear systems that have distinct eigenvalues. And what we proved last time is that for a vector of observables, f is equal to cx, where c is some matrix, n by n matrix. The time evolution of the vector of observables f, starting from some initial condition x0, can be written as what we call the spectral expansion. The spectral expansion consists of three elements: the eigenvalues that are encoded here in this term e to the lambda jt, the eigenfunctions phi j, and these eigenfunctions were shown to be linear functions of state, if you look at the previous lecture, and then the eigenvectors modulated by some matrix C, and the CVJ is an example of what we call Koopman modes. So the Koopman modes really change with the observable. The matrix C plays a role in describing the observable that, I should emphasize, is linear in state. So we're working on the space of linear functions in state. And that space is closed under the action of the Koopman operator, which is the key property. So we can keep working within the space of linear functions because the evolution starting from a linear function evolves into a linear function. The lambda j's and the phi j's are property of the operator, so they don't change with the observable, but the Koopman modes actually change. They're specific to the observable. And so the set lambda j, phi j, and cvj, so eigenvalues, eigenfunctions, and modes, is often called the spectral triple, or the Koopman spectral triple. Okay, so let's go for an example of this. And we're going to work with a harmonic oscillator, just a classical linear systems example. Now, of course, this one is non-dissipative. It's actually what we call the Hamiltonian system. In mechanical engineering, it's a spring mass system that has stiffness K and mass M here. And if we define omega n, the natural frequency squared is just being K over M, we get the system x1 dot is x2 and x2 dot is minus omega n squared x1. So it is well known that the solution of this set of equations is given by these harmonic expressions. So they're functions of sine of omega n t and cosine omega n t, the initial conditions x2 and x1, and the natural frequency omega n defined here. So let's now go. So this is well known as a classical solution, but our expansion here had some very specific terms: eigenvalues, eigenfunctions, modes. So let's find those and then contrast the two. So the matrix A here for this system reads 0, so there is no x1 in the first equation, 1, that corresponds to x2, minus omega n squared, 0. So let's find the eigenvalues. They're plus minus I omega n. And the eigenvectors are v1, 1 over square root of 2, 1, I omega n. So clearly we have complex eigenvalues, complex eigenvectors. And then w1 is similar, 1 over square root of 2, 1. And then we have 1 over I omega n. The reason why these terms are here is for normalization. If you remember, the inner product between v1 or vj and wj is asked to be 1, right? So eigenvectors are only defined up to a constant, and so this is a normalization requirement. And of course, v2 is just the complex conjugate of v1, and w2 is the complex conjugate of w1. So now, according to our expression on the previous page, we have that the evolution of our vector x at any time t is e to the first eigenvalue minus I omega n t, so that's lambda 1t, phi 1, that would be the eigenfunction, v1 plus e to the I omega n t phi 2 v2. All right, so let's find phi 1. We found v1 and v2, right, so far from the matrix. So these are the modes, the Koopman modes. Let's find the eigenfunctions. So phi 1 is an inner product between x0 and w1. And when we perform that inner product, it's just a simple computation to find that it's 1 over square root of 2. That comes from the normalization again. x1 of 0 plus I, x2 of 0 divided by omega n. That's, again, a complex function. Complex eigenvalues, so our eigenfunctions and our Koopman modes are all complex. And you can write it in polar form as R0 e to the I theta 0. Is the polar form of this complex number. R0 is the square root of x1 of 0 squared divided by 2 plus x2 0 squared divided by 2 omega n squared. Maybe you can almost immediately see that R0 squared is just energy divided by the stiffness. So that's an invariant, right? And then tan of theta 0 in this expression here is x2 of 0 divided by omega n x1 of 0. And you can pretty much immediately see that that's what we called in, vibration theory, the tan of a phase of that of the harmonic oscillator. So now we have phi 2 is just the complex conjugate of phi 1. It has to be so because x is real, right? So it's position and velocity. So x is a real vector. And then in order for the right-hand side to be real, this has to be the set of everything has to be complex conjugate to this expression here. So there are two complex expressions. In order to produce a real number, they have to be complex conjugates of each other. So V2 is a complex conjugate of V1, minus I omega n is a complex conjugate of I omega n, and phi 2 is a complex conjugate of phi 1. So we have that expression. And so now we certainly wrote down this expression here. We know all the items in there. And if you, in fact, represented this in real and imaginary parts form, you would get back precisely those equations. It's a longish computation, so I'm not going to do it, but if you'd like to convince yourselves, it's not so hard to do. It's a bit of algebra. So let's just check that phi 1 and phi 2 are eigenfunctions of the Koopman operator, and you will see that we'll come back to something that I indicated earlier in our introductory lectures. So I already pointed out that R0 is just energy divided by the stiffness. In other words, energy is K, the stiffness, R0 squared. Now, e to the I theta 0 is also an eigenfunction associated with eigenvalue I omega n. If you remember from your vibrations class, you could produce theta dot is equal to omega. So e to the I theta 0, when you take a time derivative of that, gives you I omega e to the I theta 0. So that's another eigenfunction associated with eigenvalue I omega n. And remember, the eigenvalues of the matrix are the eigenvalues of the operator. So yes, if you have I omega n and minus I omega n as eigenvalues of that matrix, they're also going to be the eigenvalues of the operator. And so what is interesting is that the phi 1 and phi 2 that play a role in our spectral expansion solution right? That is the phi1 and phi2 are products of eigenfunctions that we associated with eigenvalue 0. So R0 is an invariant, so it's associated with eigenvalue 0. And e to the I theta 0 is associated with eigenvalue I omega. Very similar to minus I omega n eigenvalue, where again R0 would be associated with eigenvalue 0, and then e to the minus I theta 0 would be associated with eigenvalue minus I omega n. All right, so the moral of the story is that given this system here, we could have just taken a look at the matrix here. Forget that we already know the solution. We could have looked at the matrix. We could have written down this expansion. That gives us the solution. And then phi1 and phi2 are defined explicitly here. I omega n and minus I omega n are eigenvalues, and V1 and V2 are eigenvectors. So that's an equivalent way, or maybe simple spectral way of obtaining the solution to harmonic oscillators. Now, of course, you could do this for, two coupled harmonic oscillators and so on and so forth relatively easily. You would get these general solutions for linear systems in terms of a spectral expansion. So let's now study what happens in the general case when we don't have distinct eigenvalues. So let's say we have some repeat eigenvalues. That can lead to a lack of eigenvectors. I mean, in certain situations, you can have, for example, a repeat eigenvalue lambda, and you have two solutions of your characteristic equation that are the same, and you could potentially have two eigenvectors corresponding to those two same solutions. But in general, that might not be the case. So you might not have two eigenvectors associated with a repeat eigenvalue. And so we can define the algebraic multiplicity of an eigenvalue as the exponent of the polynomial factor of the characteristic polynomial of determinant of a minus lambda I. This is typically how algebraic multiplicity is defined. So that's the number of repeat appearances of lambda j as a zero of the characteristic polynomial. As I said, an eigenvalue that repeats mj times does not necessarily have mj eigenvectors associated with it. And so we define another concept, which is geometric multiplicity, which is the number of eigenvectors associated with a repeat eigenvalue. And that is always less than or equal to the algebraic multiplicity. Yeah. So now we're going to make a simplifying assumption and say each geometric eigenspace is equal to 1. So we have just one eigenvector. And then J goes from 1 to S. That's going to be counting distinct eigenvalues of A. And M1 to MS are their multiplicities. So S is less than or equal than N, the whole dimension of the state space. So now we're going to label the basis of the generalized eigenspace EJ. So we're going to define this generalized eigenspace EJ by taking vectors Vj1 to Vjmj. And these are obtained as solutions of this equation that should remind you of the eigenvector equation. So I'll get to that in a second. So A minus lambda Ji on ith power Vji is equal to 0. Let me just write something quickly so you can get a little bit of intuition about that. So clearly A Vj is equal to lambda J Vj. That's an eigenvalue equation. And so from that, we get A minus lambda j I, where I here, capital I, is the identity matrix. So n by n identity matrix. Vj is equal to 0. So the fact is that, so this would be an equation for eigenvectors. Yeah, so Vj would be an eigenvector if it satisfies this for the appropriate eigenvalue lambda j. But if you put this on power I and put I here, then that equation actually defines generalized eigenvectors Vji. The idea is that for each eigenvalue, now you have each eigenvalue lambda j, now you have mj generalized eigenvectors. And these eigenvectors satisfy this equation here. Why is that? Let's say that you're just applying this with I is equal to 2. So we'll do so in this equation, you have A minus lambda ji applied twice. So you could say A minus lambda j I, then multiply that by A minus lambda j I. Vj2 is equal to 0. But that means this guy here is acting on something, some vector to make it 0. So clearly, this must be in the span of the eigenvector itself. Let's call it Vj1. Yeah. So you can easily choose that this is just Vj1, the eigenvector itself, and then A Vj2 is equal to lambda j Vj2 plus Vj, I minus 1, which in this case is just 1. That should give you an impression as to why generalized eigenvectors satisfy this equation. All right. So this is true for, obviously, for I is bigger than 2 as well. Let me erase this as well. There we go. Okay. Now we are going to define phi ji as an inner product between, so phi ji of x as an inner product between x and wji, which is the set of dual generalized eigenvectors. So j is the label for the eigenvalue, and I is the label for the generalized eigenfunction. I can go from 1 to mj, where mj is the multiplicity. So here is the generalized eigenfunction, and wij is the dual basis to vij. That can be derived to satisfy a star wij is lambda jc wji. So the complex conjugate of this eigenvalue comes in like before. But then we have plus wji plus 1. So note the eigenvectors in the hierarchy satisfy this equation where vji minus 1 is featured. the dual eigenvectors feature wji plus 1 in the equation that they satisfy. And so for I is equal to mj, we get the dual eigenvector itself, and then you go down the ladder down to 1. Here you start with an eigenvector, so vj1, and you go up to the mj. So your I goes all the way up to mj, so you're going up the ladder of generalized eigenfunctions. All right, so now we have generalized eigenfunctions. And so let's take the time derivative like we did for eigenfunctions before. That gives us x dot inner product with wji. X dot is ax. Use the adjoint to turn it to the other side. So that gives us inner product between x and a star wij. A star wij from this equation here is lambda jc wij plus wji plus 1. So that goes here. Lambda jc. So now we do inner product separately for each term. So we have x and wij. And lambda jc goes in front. Again, property of the complex inner product is lambda jc goes in front like lambda j. And so you get lambda j x wij from this part. And then take an inner product of x and wj I plus 1 over here. But this we have defined to be phi j I plus 1 of x. That's a generalized eigenfunction. So if you put I plus 1 here, that's precisely what you're going to get. All right, to continue. So these phi ij's are called the generalized eigenfunction of the Koopman operator at eigenvalue lambda j. So look how the dual eigenvectors are satisfying this particular equation, and that's mirrored in what the generalized eigenfunctions satisfy. All right. So now a little bit more intuition. Let's justify the name generalized eigenfunctions a little bit. So because when we define generalized eigenvectors, this was defined through the dual. So when we define dual eigenvectors and generalized eigenvectors, this was defined through really properties of the matrix A. But here we just define these objects, and we call them generalized eigenfunctions. So let's justify that name a little bit, because there is an underlying operator associated with these objects. So let mj is equal to 2, then the equation that we just derived reads phi j dot 1 is lambda j phi j1 plus phi j2. That's this equation here, replacing I with the 1. So phi j2 is an eigenfunction. Remember, mj is equal to 2, so the top thing is an eigenfunction at lambda j, satisfying phi j2 dot is lambda j phi j2. That's what an eigenfunction satisfies. The generalized eigenfunction satisfies this, and for eigenfunction again, we're going down the ladder. We start with the mj, and then we go down the ladder all the way down to 1. So since we have mj is equal to 2, we're going just one step down. And so now take d over dt minus lambda ji acting on phi j1, and that's going to be phi j2, because what we wrote here is just we rewrote this equation by taking this term to the left-hand side. And so that tells you that really what phi j1 satisfies is d dt minus lambda ji applied twice or squared, phi j1 is equal to 0. So phi j1 itself is in the null space of the differential operator d over dt minus lambda ji squared. And so this part here is just the derivative, directional derivative along trajectories. So it's associated with the Koopman generator. And this part here is lambda ji. That's the part that comes from asking for eigenfunctions and generalized eigenfunctions. And therefore, it's really the same, kind of the same if you replace, if you think of this thing here as A, as your generator, it's really the same as the way we have defined generalized eigenvectors, because they were asked to satisfy this analogous equation here where d over dt was replaced by A here. So it seems we have, we have the right to call these objects phi generalized eigenfunctions. And in general case of mj, arbitrary mj, it's this operator to power mj acting on a generalized function that is null. So hopefully that provides a little bit of additional intuition. And this is a theorem that involves a longer computation, so I will not prove it, but you have it proven in the notes. And so the general solution of our problem in the case when geometric multiplicity of every eigenvalue is 1. So the general solution of our linear system in the case when geometric multiplicity of every eigenvalue is 1 is given by this expression. It's a little bit more complicated than the previous one that we had. In the previous one, all the mj's were 1, so we didn't have any differences there. But we had the lambda j, the eigenvalue. We had the eigenfunction. Here we have generalized eigenfunctions. And then we had the modes that were really eigenvectors. And in this case, they're generalized eigenvectors. We certainly didn't have the second part, and that's the part that contains algebraic terms in time. So these are the terms that that can grow algebraically, but they also contain generalized eigenfunctions and generalized eigenvectors. So provided we can find the generalized eigenvalue, generalized eigenvectors, and the eigenvalues themselves, we can find the general solution to evolution of a linear system, kind of directly from Koopman operator theory. I'll re-emphasize that as long as we restrict the space of observables to linear ones, so that's in general an inner product between some constant vector and x, then the generalized eigenfunctions and the eigenvalues of the Koopman operator are obtained from the standard linear analysis of A and transpose, as I've shown. And then also this restriction to the case when geometric eigenspace is 1 is not really fundamental. Let's suppose that we have an eigenvalue that has algebraic multiplicity 4, but it has 2 eigenvectors associated with it. Then we take the first eigenvector, we find the generalized eigenvectors associated with that one, and then we take the second eigenvector and the generalized eigenvectors associated with that one. So there is really, it's a simple extension to treat the case when geometric multiplicity is larger than 1. And now that we have in hand the spectral expansion, we can start talking about some geometrical properties of the underlying dynamical system. In this case, still a linear dynamical system, x dot is equal to ax. So the key objects in the geometric study of a linear dynamical system like this are the stable, unstable, and center subspace. So just a reminder, a stable subspace of the fixed point of this system is the location of all the points that go to the fixed point at the origin as time goes to infinity. And classically, we obtain it as the span of generalized eigenvectors corresponding to eigenvalues of negative real part. The unstable subspace of the fixed point is the location of all the points that go to the fixed point as t goes to minus infinity. And classically, we obtain it as the span of generalized eigenvectors corresponding to eigenvalues of positive real part. Now, the center subspace, we don't define by asymptotics. But what I mean there is that stable and unstable subspaces are defined as limits when t goes to infinity or t goes to minus infinity. But the center subspace is usually defined as a span of generalized eigenvectors associated with eigenvalues of 0 real part. So everything here depends on eigenvectors. And so what is interesting is that I mentioned in the spectral expansion, like this, these objects here, the generalized eigenvectors, they're not actually associated with the operator, Koopman operator. They're associated with the observables. And so somehow, in classical dynamical systems theory, we are defining these objects in the state space, and we are defining them based on objects, eigenvectors, that would potentially change if we change the observation. And so what I'm going to show you is that when you take up the spectral expansion point of view, you can define these same subspaces, but using objects, in particular Koopman eigenfunctions, that are the properties of the operator itself and not the observation. So let's pursue this. And again, let's simplify a little bit so that we don't have to use that expression that also had algebraic terms. Let's assume that A has distinct eigenvalues. So we have a simple spectral expansion of the state observables that is sum j is equal 1 to n, e to the lambda jt, phi j of x0, vj. So this is just expanding or finding the values of variables, state variables x1, x2 to xn at time t, starting from some initial condition x0. So let's start by ordering the eigenvalues lambda j from the largest to the smallest, and then u, c, and s are going to be the number of positive real part eigenvalues. So u would stand for unstable, and then 0 real part eigenvalues, so that would be c for center, and negative real part eigenvalues, which would be s. So clearly u plus s plus c is n. So the number of eigenvalues is n, and so these three numbers need to sum to n. And then lambda 1 to lambda u are the quote-unquote unstable eigenvalues, so it was the real part. Lambda u plus 1 to lambda u plus c are center, so 0 real part eigenvalues. And lambda u plus c plus 1 to lambda u plus c plus s would be negative real part eigenvalues, or let's call them stable eigenvalues. So now take an initial condition, x0, such that phi 1, the eigenfunction associated with lambda 1, to phi u plus c of x0 is equal to 0. So we're looking for the joint 0 level set of eigenfunctions phi 1 to phi u plus c. So all the unstable and all the center eigenfunctions. This is the set. So x0 belongs to this set, provided that all of these eigenfunctions are 0 for x0. And so from the expansion, spectral expansion, since many of these eigenfunctions are zero, in particular, all the stable, all the unstable and the center ones are zero, we can sum only over the eigenfunctions in this expansion that are in fact such that their associated eigenvalue is less than zero. Okay, so that's the solution, what the solution looks like, starting from an x0 that satisfies this property. And so if you look at this, all the lambda j's that are in this expansion now, the real part is less than zero, and therefore this is going to go to zero as time goes to infinity. And by definition, then x0 must be in the stable subspace. All right. So now we proved that if x0 satisfies this property here, so it's zero, it's in the zero level set of unstable and center eigenfunctions, then it's in the stable subspace. Let's do the converse. So assume that x0 is in the stable subspace, and also assume that our expansion contains a term such that the real part of lambda j is bigger than or equal to zero. So something like this, but not summed over all real part lambda j less than zero. There is at least one in which it's bigger than zero. Now that term will not decay to zero as time goes to infinity, and therefore limit when time goes to infinity of x starting from x0 is not equal to zero. And so x0 is not in the stable subspace, but that's what we assumed. So we get a contradiction, and therefore all the initial conditions x0 that satisfy this condition, in fact, give you the whole stable subspace. So instead of characterizing the stable subspace as the span of the stable eigenvectors, you can characterize it as a zero level set of the associated Koopman, of the Koopman eigenfunctions associated with unstable and center eigenvalues. All right, so now it's intuitive that now if you pick the stable eigenfunctions and center eigenfunctions, then and set them to zero, then such x0 that would satisfy all of these conditions would characterize the unstable subspace. The proof is pretty much the same, and we can proceed along the same line of ideas and say, okay, it seems like in order to find the subspace, we need to set all the eigenfunctions that don't belong to eigenvalues associated with that subspace to zero. So if you want to define the center subspace, then you set all the unstable eigenfunctions to zero and all the stable eigenfunctions to zero. So that's the way of characterizing center, stable, and unstable subspaces without referencing eigenvectors or equivalently Koopman modes. And the theorem that follows with what we've just stated is if we have a linear system, then the stable subspace is the zero level set of unstable and center eigenfunctions. The unstable subspace is the zero level set of unstable and center eigenfunctions, and the center subspace is the zero level set of unstable and stable eigenfunctions. The beauty of this result is that it generalizes nicely to nonlinear systems. Namely, when you take a linear system and you perturb it, you can still discuss the behavior, or rather the stable, unstable, and center manifolds of the resulting nonlinear systems. You can characterize it still with as zero level sets of some of certain eigenfunctions of the Koopman operator. In the standard treatment, of course, the only thing that one claims is local unstable stable and center manifolds that are tangent to the span of eigenvectors. But as you will see, this new definition is going to allow us to actually talk about global stable, unstable, and even center manifolds for the nonlinear systems. And thus, we remove this obstruction of local analysis that is really strictly due to relying on eigenvectors of the linear system, because in the nonlinear system, of course, the nonlinearity prevents us from defining such objects. What we do maintain in nonlinear system as well is the notion of Koopman modes, but there is not only n of those. The expansion, the finite dimensional expansions that we have here that are of this type turn into infinite dimensional expansions in the same way as when you're doing Fourier analysis, and instead of a sinusoidal signal, you have some kind of a square wave, and instead of a single frequency, you need to use harmonics of that frequency. You'll see that the analogy is pretty potent, and that in the context of linear systems, we can get away with having n terms of our expansion. In the nonlinear systems, we can, but we can still have a spectral expansion that is quite valuable and enables us to define these geometric objects like stable, unstable, and center manifolds. Okay, here is a simple example. Let's consider the system x1 dot is minus x1, x2 dot is x2, and x3 dot is x3. The matrix A is diagonal. Minus 1, 1, and 1 are obviously the eigenvalues. And then the solution is defined as this spectral expansion where I have replaced phi j's with xj's, the initial conditions, because the eigenvectors being 1, 0, 0, 0, 1, 0, and 0, 0, 1, when you inner product x0 with that, you get exactly xj of 0. So here in the Koopman spectral expansion, we will have phi 1, phi 2, phi 3, but they are actually initial conditions in this simple case, x1, x2, and x3. Now, consider the set of initial conditions such that phi 2 and phi 3 are equal to 0. That's just that x2 of 0 and x3 of 0, right, are equal to 0. So in other words, x0 is x1 of 0, 0, 0. So look at the first equation, and you're going to see that that kind of an initial condition is going to decay to 0, and that gives you the stable subspace. And obviously, the unstable subspace is obtained by making phi 1 0, and so any vector of the form 0 x2 x3 is in the unstable subspace, and that's obtained by asking that the stable eigenfunction is equal to 0 for that set of initial conditions. So that's a simple example that gives us that particular result. Okay, we're going to stop here, and then next time discuss the notions of conjugacy and semi-conjugacy.